One of the main reasons that we've been talking about transformations is so that we can see figures in a plane and understand that we can manipulate their orientation to help us logically make sense of a relationship. Say, for example, like a square. I have a proof here. We're going to prove that the diagonals are congruent in a square. So the diagonals, if we have a square, the diagonals are the lines that go through the square, right, from point to point, make like an X. We want to prove that they're congruent in a square. So here's some thought processes I want you to think about. So logically speaking, when we have a coordinate grid, we know that the axes are perpendicular to each other because one axis is horizontal, one's vertical, and horizontal and vertical segments are always perpendicular to each other. And it's nice for us to see scale on these horizontal and vertical axes, right? Which we can just translate the axes out to the grids on our coordinate grid here, right? We know that each of these units are also 1 or whatever we want to scale them to. So if I want to construct a square, what's nice about the coordinate grid is, and I'm going to use my polygon tool, I can use the axes to help me guarantee perpendicular, right? And so if I put a point on the origin, for example, and I want to make a square, say side length 5. So there's a segment with a side length of 5. Let me move this down a little bit. So boom, boom. So then I need another length of 5. So I'm going to go up to this point here, put a point at 0, 5, and back down. So there's my square. Okay, it's got 4 90-degree angles because of the horizontal and vertical nature of the coordinate grid. I know that for a fact. And I can see from scale that each side is 5 units long. So that's got to be a square. And then we can check to see if our segment, these diagonals now, if they are the same length. So when you think about segment length, I want you to think about translating, say, this endpoint right here to this endpoint here. How did it move? And same deal with this endpoint here up to this endpoint C here. How did it move? And if our movements are the same, Pythagorean theorem is our argument to say, well, like B, for example, if it translates to D, it has to go 5 units to the left and 5 units up, right? So that's got some length here. It's also, we could find that length if we want from Pythagorean's theorem. We would take 5, this length 5, square it, so 25. This is a length of 5, so if we square it, we also get 25. So if we add up those sides squared, we get 50. So then the diagonal then right here must be the square root of 50. Same deal if we look at this diagonal, we can go, okay, well, A had to translate 5 units to the right and 5 units up. Well, those are basically the same, it's the same distance it has to translate. Therefore, these lengths will be the same. This will still be the square root of 50. And we can just prove with that square that the diagonals are congruent. But what if we want to talk more general? Okay, so for instance here, how about any square? We need one example to argue that the diagonals in any square are congruent. So what I have here is a segment that I can move around. I made its length unknown, so I used a slider so we could change length. We don't really know the exact length of this segment here. But here's how, again, we can use the coordinate grid. Now we don't have scale, but we do have the very basics here, a perpendicular relationship. So again, if I put an endpoint on the origin, and I'm going to put B either vertically, I might want to move this down. I may want to put B on this y-axis, this vertical axis here, okay? Or I may want to put it down here. It doesn't really matter. I'm going to put it right here on the x-axis. Okay, so now I want to check to see if now the length of this segment, and the reason that we want to use the origin, we know the ordered pair, the location of A is at 0, 0. Now, the length of this segment is going to be A, which is the length of A here that determines the length, right? So I can think about the ordered pair or the location of, say, this point B. It's x coordinate, how far it moved from the origin, must be this length, right? The length of whatever a is. So it went out a units, and then its y coordinate's got to be 0 because it's on the x-axis, right? So now what we want to do is put a point up here that's a units long, and its x-coordinate has to be 0, right? So 0a would be the point that we want up here. Well, to guarantee equal length, I'm going to grab my circle tool, center a circle at the origin, go out to B, so that intersection up on the y-axis has to be the exact same length. Oops, and I missed it. I keep missing that. There it is, black point, that's what I want. So that point right there has to be the same length, right? Because these are radii of the same circle. So that's guaranteed to be A. And if you think about it, its location or its ordered pair, it didn't go any left or right, so the x-coordinate's 0. And it went up the same length as this segment, so it went up A units. And then to find our square, wouldn't we have to go over A units, like B here, and up A units like C here? So wouldn't this be at like A? So I'm going to put a point here in my input bar, an ordered pair, so I'll use parentheses and call it A, comma A. And I'm going to hit enter and check it out. Look where that point went. So we know that its location, whatever A happens to be, this is where that point goes. So now I can make my square of any size. So when I move A around, notice that stays a square no matter what, right? And whatever the length A is, this is going to be what A is. All right, it's going to go over A and up that length of A. So now let's look at our diagonal length here. Distance formula would say, well, A had to translate to go to D up here, looking at this diagonal right here. A had to go over A units and up A units. And then this point here, B had to go to C, A units to the left and up A units. So therefore, by Pythagorean's theorem, those lengths are going to be the same because their directions that they translated are the same. So no matter what size, that's what A means, no matter what size our side of our square is, then we know the diagonals will always be congruent to each other in a square. So that's what's nice about coordinate logic, using that perpendicular relationship. Now let's look at a problem like this. Standard position is this position where we use the origin as a point and we put a side along the x-axis. That's what we call standard position. We make a shape have a horizontal line because horizontal and vertical is very easy for us to use logically. So I have a triangle here. I want to put it in standard position and then determine whether it's a square. So when we have diagonals here, it makes the math a little bit harder. We don't really know for a fact that these are equal in length. So let's put it in standard position and check it out. Okay, the square has this shaded interior, so it's a polygon, and I can transform this square, potential square, we'll call it a quadrilateral for now until we know it's a square. I can transform this so that I can get it to the origin and rotate it so that we can get one of the sides to become horizontal, and I'll show you what I mean. So the way that I view this square is I want to put this point here at the origin. So I'm just going to translate, I'm going to grab my vector because I want to translate this point to the origin. So there's my vector, right? So now I'm going to go to my transformation toolbox. I'm going to grab my translate by vector tool. I'm going to click on my polygon, click on my vector. So now I just translated this shape to the origin, right? These are congruent in size. This square is the same as this square. Lengths are the same, area, everything, right? So now our angle, I'm going to put a point right here. Oops. Okay. So now if you can see that this is going to be my angle that I want to rotate. I want to take this side and rotate it so that this side maps exactly onto the x-axis. So to do that, I need to figure out what this angle is. I don't have a point on the x-axis yet, so I need to put one there so I can use my angle tool. And now I'm going to grab my angle tool and I'm just going to measure what this angle happens to be. 17.24. So now I know that I can rotate. I'm going to go back to my transformation toolbox, grab my rotate tool. I'm going to rotate this square around the origin. That's my center of rotation by that angle. Happens to be 17.24 degrees. And which way do we want to rotate? It's got to come down, which is a clockwise direction. So I'm going to click OK. So there's my square now that's congruent to this square. When we translate, we rotate, we reflect. The shapes always stay congruent. Sides, nothing changes, just orientation. So now this square here that I'm checking, this original green square, this one, I got it now in standard position. I'm going to hide this quadrilateral. So I put this square in standard position, and we can see that we have a length of 4, this is at 4, 4, so yes, that must be a square. Okay, one more example of this, and then I'll be done with this video. Let's put this triangle in standard position and determine whether it's isosceles or not. So looking at this, maybe this side AD and this side AC, these are the two legs, the two sides that are congruent in the isosceles triangle. So what I'm going to do is I'm going to take this triangle here and I'm going to put the base. This is known as the base, the side that's not equal to the legs, the base. And I'm going to make it the base by making it the horizontal segment right here. And we'll check out in standard position whether we can determine if this is isosceles or not. So I'm going to take this point C, I'm going to translate it to the origin as 0, 0. So I'm going to grab my vector tool, click on C, it's going to go to the origin, so I'm going to click on the origin. Now I'm going to translate. Now, notice we don't have the interior of this triangle. It's not shaded, so this isn't a polygon. It's just segments right now. So since it's not a polygon, then I have to highlight everything. So all of that stuff. And now I'm going to translate that by this vector. So there, I just translated this triangle. And now, since this side right here is what I want to be horizontal, I want to get this side to rotate onto the x-axis. So I need to find out what this angle is right here so I can rotate by that angle. So I need to put a point on the x-axis now. I'm going to measure this angle in a clockwise direction. Vertex is always the middle point. 80.57. So now I'm going to grab my rotate tool. I'm going to select everything I want to rotate, not that vector. So I'm going to hold control down. Since I have everything selected, I'm going to hold control and deselect my vector. Oops, that didn't want to work there. Let me try this again. Try not to get my vector in there. Oh well, I can just hide that vector. So anyways, I got my my triangle selected here to rotate. I'm going to click on the center of rotation, which is the origin now. I'm going to change my angle to this 80.57, the angle necessary. It's going to rotate clockwise, and boom. There's our triangle that started out in this position. We transformed it to get to standard position, and now I can check to see if this is isosceles or not. And it looks like to me, I want to get rid of this triangle here. Oops. Okay, sorry about that. But here's our triangle now. And I bet you if we cut this in half, I'm going to use my perpendicular line tool and see if it helps our eye out. Perpendicular bisector. So if this is isosceles, the perpendicular bisector of this segment should go through that point, and it does. So therefore, this is an isosceles triangle. But we can see in standard position, because we made it horizontal, much easier to see. Okay? So good luck trying to get some of your shapes to transform in standard position.